Hello everyone. In this session, I'm going to look at how we can really use the concept of decision trees which we have discussed till now for understanding survival analysis. Survival analysis, as the word itself is very clear, we are trying to look at time to survive, time to event. In general, if I have to talk about it, it's time to event. So probably I can say very common usage is time to death. In the mortality studies, we can use it for time to death or time to survive a particular disease, right? How long a person has fought a disease before he was dead. The time from the time the person is admitted into the hospital, right? Either he would have recovered and he would have left, or he would have died somewhere. So what is the time? One for death, two for survival, or three, sometimes in the middle, he would have left the treatment process altogether. Those kind of data are called as censored. So with the presence of all these things, I really want to assess the time to survival for a particular set of people for a particular event. So that is what is survival analysis. And if I have to differentiate between two groups of people, let's say people with diabetes versus people without diabetes, I'm talking about time to survival from a particular disease. I want to really assess, is there any difference in the time to survival for a particular disease for a person, for people with diabetes versus people without diabetes? In those cases, I'm bringing in the decision trees. I'm trying to build a tree, I'm trying to build a survival analysis model, not a universally, not a universally similar kind of a model, but for different groups, I wanted a different survival analysis model so that I can even compare the impact of such kind of factors on the survival factors, right? So that is what we are going to look at. How can really the decision trees help us in performing survival analysis? Initially, we will try to understand the basic introductory aspects of survival analysis and the decision trees, and today the need for using the decision trees in the survival analysis. Then we will be talking about two important algorithms in this context, right, which can be implemented quite comfortably in R. So again, our focus here is more on implementation in R. Once we have understood the basic concept, we will not get into the mathematical part of it. We will look at the implementation in R, and whatever the response that we get, how do we interpret the same for making a decision. So this is where I am going to look at the exponential algorithm as well as conditional inference survival tree algorithm. So we will differentiate between these two as well and see, we'll take one single example. Here the example that I'm going to look at is nothing to do with the diseases, survivals, etc. I have taken some data again from the world of cricket. So specifically the one day international cricket, and within that all the innings that are being played by Virat Kohli. I have taken a list of all the innings that have been played by Virat Kohli till date, and within that, let me load the data so that you will get a clarity on my question once I create the question. So this is the data. So let me load that data. I'll showcase what is there as a part of this Virat. So number of balls he has faced in all the innings that he had played till now. what was his strike rate in that particular game, right? Per every 100 balls, how many runs he has scored, at what position he has batted, in what innings. One means India batted first in that match, and two means India batted second. Then we have opposition, home or away indicated as A or H. Status. Status of one means yes, he was out in all these matches. So if I look at it more similar to a death in a mortality study, so these are the scenarios where the event has actually occurred. The event is out here. Here I am looking at the event being out. So time to event is nothing but how many balls typically he has taken to get out. So he has taken 22 balls to get out, 67 balls to get out. Whereas 0 indicates, no, he did not get out. So 0 is a kind of a not out, which in this case I will take it as a censored data, because I don't know when he would have got out in that particular match. He has faced 2 balls and he was not out, but we don't know when he will get out. That is what is the censoring all about. So we have a censored data there. So that all the censored data is shown with a status of 0, and all the data where the event has occurred. Here the event is getting out. So basically here time to out. If this problem has to be framed properly, it is a time to out problem, or yes, more specifically here the time is tracked in terms of number of balls to out, right? So that is what is the problem out here. I am more interested in taking this as a time variable and this as the status variable, which is showing whether he was out or not out. Ones are the event has occurred, 0 is the event did not occur, and the data is more of censored. Now what we really want to see using the decision tree, if I don't have the decision tree and if I have to build a straightforward survival model, I only need these two things: ball space, status. Because ball space is the time and status is more associated with whether the event has occurred or the data is censored. Those two columns are sufficient if I have to build a general survival analysis model. But now a decision tree in terms of partitioning, I want to do it based on, let's say, the opposition, or let's say the innings, let's say home versus away. I really want to see whether there is some level of a significant difference in the survivals in the time to out that is happening, let's say in home versus away, or let's say in first innings versus second innings or something, so that I can really make some kind of conclusions about this particular play, right? So let's look at let's go ahead and work out on this data. First of all, getting into the introductory aspect of survival analysis today is just not restricted only to the medical field, which earlier used to be the case, right? Where the major usages are time to death or time to recover from a particular disease, right? So there are so many such kind of instances which were earlier used, but today any time to event we can think of from many industries, from many dimensions, from many areas of research. We can very well use the survival analysis model. So we are talking about the time to survive, time to fail, various other aspects regarding that. Earlier, for doing this, there was a mechanism called Cox proportional hazard regression model, which is more like a semi-parametric kind of a model. So earlier we would have used the Cox regression for modeling various survival analysis model, like There, I could have taken age of the person into constraint, or probably the gender of the person, and based on that, the time to survive, the probability of survival would have been computed separately. So we had a list of parametric and semi-parametric models, wherein the various covariate effects like age and all, which are continuous variables, I have used all these things as input parameters, and a regression model would have been built, and based on that a statistical inference can be created, and which can very well be used for making interpretations regarding the probabilities of survivals, etc. So in this case, what is happening is it's a specific link that is getting created between the age and the death. So we are forcibly trying to put a link between the covariates, which are the age, and the death, which is the response variable. And this kind of relationships, they are not identified by default. They have to be explicitly specified by the analyst. Now, this is what was one of the limitations of the typical hazard-based proportional hazard regression models, which use a combination of parametric as well as the semi-parametric approaches to do the modeling of a survival variable. But when we are getting into a survival decision tree, so here we understand survival model is a simpler one. But if I have to partition this survival model, let's say age based, gender based, and income based, etc., one thing is I can use a Cox proportional hazard model, which tries to fit in some kind of relationship between the hazard, which is the survival or the death element, versus these various covariates. We are trying to force relationships between them, and we are trying to create different equations in case of a proportional hazard model. But in the place of proportional hazard model, I can very well think of using a survival decision tree, right? The splitting, the partitioning of the survival models across the different groups of data. That is what is happening in a Cox proportional hazard model. We are trying to look at the survival part, the time to event part, not for the data as a whole, but for groups of data separately. So the Cox proportional hazard model is one such kind of a helpful thing, where a parametric and semi-parametric combination can be used there. Whereas in a survival decision tree, which is an alternative to Cox proportional hazard regression model, it is allowing the data scientists, without putting any kind of a link, right? Even if I don't know how age is related to the death of the person, or even if I don't know how gender is related to the death of the person, I don't need to forcibly fit any kind of a link between the response variable and the covariates, right? I really don't need to know what is the kind of interaction that is existing between these two variables. So which means there is a much greater flexibility that is there for me, and even the detection of the relationships is done automatically. I don't need to specify the relationships in advance. Based on the data that I have, so even if I assume that there might be a relationship based on, let's say in our case, the number of balls faced, right? That is what we are calling as a time to event. Let's say that might be differing based on home versus away. Or I may be saying, no, that might be very much differing based on whether he is playing in the first innings or in the second innings. Now, I really don't need to give all these relationships explicitly. If I give a list, it can identify the scenarios where the influence is existing and where the differentiation does not exist. So prognostic grouping is something that is coming out as a natural output from the survival trees. So that's one reason compared to Cox proportional hazard models, we can very well think of relying on the survival decision trees. Now, to execute this survival decision tree, there are a couple of algorithms. So in R, we will try to use this exponential algorithm. So here the assumption is the time values, in our case the ball spaced, right? Because we have taken the ball space for this example. Ball space is the time related part here, time to out, ball space to out. So the time values are assumed to fit an exponential model here. So I am assuming that they are fitting an exponential model. For that, we will install the package rpart, and I will use the rpart function again here. Okay, so let me get started with my analysis out here. I am installing the package rpart. I think we have installed it earlier, so let me directly load it. That's much better. But if you have not installed it, you installed it, because we have used it for other topics earlier. I have already installed it, so the R part is directly loaded out here. And just for information, we'll look at the R part function to see what it typically offers for us. If you see, it is fitting an R part model. Now, one, I have to give formula as an input. The formula is the dependent variable versus the explanatory variables. So I can very well give that right now. First, let me set the data right, and then I'll give it. So the formula is something that I have to give with a response but no interaction terms. So no stars and no colons. Only the pluses are used as separators, right? Then the data is something that I have to give with to interpret the variable names in the formula. So I have to give the name of the data, the weights, if at all there is a weight that are assigned, right? If I'm taking only a subset of the data, then I have to give that. All right, the method. In method, I can have any of these four methods: ANOVA, Poisson, class, or EXP. So here we would be using EXP, but one of these four methods I can use. So four different kinds of models are getting picked. First of all, let's understand this is recursive partitioning and regression trees, R part. So if the method is missing, then the routine tries to make an intelligent guess if I don't give a method. If Y is a survival object, then it's better that I use EXP. If Y is a survival object, that's the reason I am giving EXP. If Y has two columns, then the method Poisson is assumed. If there are two columns per Y, then it assumes the Poisson data. If Y is a factor, then class is assumed. This is where we have used it for classification algorithms. Otherwise, method equal to ANOVA is assumed. So you could see here, this is for continuous variables. This is if the response variable is a categorical variable. If the response variable is a time to survival kind of a variable, then it will use EXP. And if it is having two columns, then it is using Poisson. So here we will specify the method as EXP directly. That's it. So based on this, I will get an exponential algorithm for the time to survival kind of a data, right? All right. So let me go back. So that is what it is. So here the few things that I have to mention. One, Z is a survival response variable. So it should be a survival related stuff. But in our data, we directly don't have a survival variable. We have two columns. One is the ball spaced and two is the status. So basically, one we have time to event data, two the status of the event. So these two put together will actually create a survival object. So you see here, by taking these two from the data, time to event, in this case the ball spaced, status, whether the event has occurred or the data is censored, based on these two. So in this case, I have to always specify whenever the event has occurred, I want to set it as 1, and whenever the event did not occur and the data is censored, I will take it as 0. So I will create Z is survival, time and status. Survival object is constructed using the survival package. So I have to load the survival package as well, because I will construct the survival object now from this data. So we have loaded the survival package as well. The data is the data set containing the explanatory variables, and the method I have to set it explicitly as exp, which will indicate a survival decision tree. When I'm setting the method as exp, that itself indicates that it is a survival decision tree. So in this case, I have to first load the packages, which I have already done. rpart and survival, both the packages are being done. Then I have to get the data. We have already loaded the data Virat. Let me perform some basic summary on that Virat to see if there are NAs or some such kind of stuff. I don't think there are any. Right, the strike rate is actually looking like a string variable. I don't know why. We need to really see that factor. The strike rate is looking like a factor, whereas it has to be a number. All right. Then the ball space, okay, it's a number from 0 to 148. Position, yes, 1 to 7 positions he has played. Innings, first or second. Oppositions, we have different set of oppositions out here. Home or away, 103 away and 65 home. Statuses, there are so many zeros, ones, but yeah, more number of ones because the out as an event has occurred. Right? Okay, so only the strike rate is having a problem. Either one, we can ignore that strike rate as a part of the model for understanding purpose, or again we have to go back to the spreadsheet and see why it is showing me uh, as a string, right? So probably let's do one thing for quick observations. Let me quickly look at how this data is. So let me take Virat $SR. Oh, there is one place I think the hyphen is there in the data, right? So that is what could be the reason. Let's do one thing. Then I'll take Virat as again Virat. I'll take a subset of Virat where I'll consider all the columns, but the rows wise where I will consider Virat $SR, Virat $SR not equal to the hyphen. Right, I'll set it as Virat $SR not equal to hyphen. This is what I will set. That would be the rows that I want to consider, and I'll consider all the columns. Let's see what is happening. Now what is happening with the dim of Virat? How many rows, how many columns? There are 167 rows and 7 columns. Earlier, what was the situation? We don't know. So let's see first of all whether that whether that strike rate has typically gone off. Yeah, looks like in the data that strike rate is not existing. So what I can very well do is Virat dollar SR, I'll consider it as dot numeric, as dot character. First, because it's a factor, I'll convert that factor into uh, first into a character, and after that I'll convert it into numeric. First, the factors are getting converted into characters, and those characters are getting converted into numbers. Now let me just check the summary of Virat. Okay, now it's looking much better. The minimum is 0, the maximum is 209, right? The first quarter, third quartile. So it's looking like it's a numeric data. So let's use this data rather than the one where it has taken a hyphen in the data. So let's ignore that record, all the other things. Let's go ahead. Okay, so we got the data. We did a preliminary inspection of the data using the summary. No NA values, no weird values like we had in case of strike rate. We have removed that weird value from the data as well. If required, I can very well perform the transformations of the response variable or the explanatory variables. If at all, in some cases, I want to play around using the logarithm of the time instead of directly taking the time. So I can very well do all those kinds of activities. But yes, now the major part comes in, wherein I have to create a survival object based on the time and the status. So let me create one survival object. I'll take a survival object called Z, right? Wherein I am creating the survival object with two variables. One is the time variable and the second one is the status. So let me take the time as Virat dollar BF, the ball space, that's the time variable, and Virat dollar status is the status variable out here. Based on this, a survival object is created. If I look at the survival object, there is nothing specific, right? The only thing it creates in a kind of a way that the survival models understand 70 plus 2 plus 104 plus. So it's basically nothing but the ones are where the event has occurred, the number would be taken as it is. Where the event did not occur, it would be appended with a plus. That's the major thing that happened. And much more than that, when I look at the class of Z, right, if you just supply the data like this, it doesn't work. Because if you look at the class of Z, it's a serve class. So I have to really convert, even if I provide the data in this format, the class of it needs to be a survival class. That's the step. Then, now we are ready to fit the decision tree, because as a part of the decision tree, the inputs that I require are Z should be a survival variable. Now I got my survival variable. Now because of this, I am ready to fit my data. And now I can very well talk about the different variables which can influence it, where I want to do the bifurcation as well. So let me call it as fit survival. That's the name of the variable that I'm using. I'll use the rpart function for this. Z is my response variable. So as a part of my input variables, I don't know. So first let me take the position, or let me take innings, first versus second, or even I would like to take the opposition. I can go one by one actually. Opposition is too big, so probably let me take it separately. Home, away. So some set of variables. and the data in this case for me is Virat. As I said, we need to use the method as exp. That's it. This one single line is going to fit your model. That's the simplicity. The entire survival analysis is fitted through this one single line. If you really see what it has done, FitServe, so it has done a splitting only based on the innings. Though you have given position, innings, home away, so many inputs that you have given, the tree found that the difference is very significant only with respect to innings. Nothing to do with home or away, nothing to do with the position. Only with respect to innings it has considered. So the tree has built separately innings greater than or equal to 1.5, which means the second innings versus the first innings. So when he has batted second, his time to event was slightly different from when he has batted first. That's the major thing that has come out through this survival analysis. And I can very well get a plot of this fitment altogether. So I'll do the plot of the fit survival model, which clearly brings out, I have to put the text in it as well. So it says innings greater than or equal to 1.5. So we have to really make some small modifications to this tree, wherein we'll get the n values as well. So let me do one more thing. Let me do the plot again. Now the text wise, along with this model, I would also say use dot n equal to true, so that I'll get the n values. How many of them are falling in this group? How many of them are falling in that group? Then I would also, because the size of the text is too big, I'll actually make it some 75% of the original by setting it as 0.75, and I'll display all the values. So this is where I'm getting all equal to true. So now you could understand slightly a better representation out here. Innings greater than or equal to 1.5. There are 142 out of 167 altogether. And what we could see is the difference is quite clear. Here it is 0.85 versus 1.215. Now we'll understand what these two differentiations are more like. You could see here in this output that it has given, the split is innings greater than or equal to 1.5. There are 95 such innings less than 1.5, which is the first innings. There are 72 such kind of occurrences. The deviance is 130 here, the deviance is 70 here. The y value, right? The y value, we are talking about a survival object. So here it's coming out to be 0.85 and here it is coming out to be 1.21, and it's a terminal variable because it is denoted by a star. Now we have plotted terminal nodes report the estimated rate. So we have got the estimated rate as 0.85 in case of the second. So estimated rate in terms of out happening is lesser. The estimated rate of out happening in the second innings is much lesser, which means the survival is much higher in the second innings compared to the first inning, right? So the estimated rate of the event, occurrence of the event, rate of occurrence of out is only 0.85. So the chances of getting out in the second innings are much lesser compared to the chances of getting out in the first innings. That is what we could see out here. And it's also giving me the number of events and observations that are available. Now for each, let's say I want to know at the node 2, I want to get the complete details. I can very well use the path dot rpath. Here of course we don't have any complex path, so I really don't need to bother too much about it. But if I really want the path dot rpath and I say node number 2, what is the scenario? It says node number 2, it is coming from the root node, and the logic for the split is innings greater than or equal to 1.5. Like that I can very well see if the tree is a very complex tree, I can very well use the path that are part to get how it has reached that particular path of the tree. So you can see the rules that lead to the set of rules which are leading to that specific node. Here, because it's only a one layered node, I really don't need to bother about what is the path that it has taken. But if the tree is a multi-layered kind of a tree, the path plays a very important role. Then we could also use the plot CP. Let's understand what this plot CP function is. It gives a visual representation of the cross validation result. So if at all we are talking about different cross validations, we can look at the relative error in the process. So I have to give an rpat object as the input, right? But it will give me the complexity parameter, especially talking about whether the differences are significant, one across the first innings versus the second innings. So I can very well do a plot CP of the fit survival data model. I can do a plot CP of this, which is telling me that this is what is the complexity parameter. The relative error is not, if you look at the relative error, it is somewhere around 1, but with a kind of if we are changing the size of the tree, the relative error is going in this typical manner. Right? So one thing we can very well look at it is if there is a big change, if there is a big change, we could see that the relative error is going to be drastically different. So in that case, there is a big need to really prune the tree quite heavily. Whereas in this case, if the difference is not that drastically changing, then there is no need to prune the tree, because you could see here, one is without doing the branching, and this is after the next branching. So there is a slight difference, but beyond and you are getting the minimum most error after doing the first branching, and because of that there is no reason to really prune the tree. The tree itself is a one layered tree. So if the tree is a much deeper kind of a tree, then looking at the size of the relative error, wherever the error is the minimum most possible, it is where we will take a call in terms of that should be the better tree. So here the size of the tree is 1, this is the relative error. Size of the tree is 2, this is the relative error. So the relative error is the lowest in this case itself. So I can very well go ahead by keeping the same tree. I don't need to really prune the tree to any kind of an extent. This is applicable only if my tree size is exceptionally long. Then I would see wherever the relative error is much lower, that is where I can think of taking a pruning on the tree. Survival times can vary differently between the subjects, but now once this survival is there, I can very well think of plotting this survival object, one for the first innings and for the second innings as well. right? Because normally decision tree analysis is useful to homogenize the data. So we have homogenized the data into first innings separately and second innings separately. So we have differentiated between the two subgroups. So here, based on the treatment, we will differentiate the subjects. Based on the innings, we have differentiated the subject. So I could have differentiated it between home and away, various other things. Whereas if there is a single tree, then it is grouping all these things and overall survival is what is being talked of. But when we are going with a survival tree, then there is a kind of a splitting that is happening based on the various grouping criterias, which could help us in understanding the survival models in a much more appropriate manner. Now I can go ahead in terms of doing the plotting of the survival based on the final notes, right? So I can very well do the plotting of that survival. So for that, I can very well consider, let's say I want to look at the survival model. So first let's do a survival fitment. Let me use some variable km. We will use as survival fit as a function. Let's use what this survival fit function is going to do for us. This function creates survival curves from either a formula, either I can give a formula. So this is where I will take the formula that we have used earlier, a previously fitted Cox model or a previously fitted accelerated failure time model. Any of those things I can give as input to it. So I am giving the formula from our the same from our same data frame. So I'll use a variable called km where I'm using surfit. The dependent variable is z, which is a survival variable, and I would also consider. So if you look at this model fit serve, right? Let's see this model fit serve again. It is giving me these are the things, right? So if I type fit serve dollar where, so it is giving me individually, right? Fit serve dollar where, if I am typing, I'll get individually all those records which particular node they are falling into. Are they falling into node 2, node 3, which particular leaf node they are falling. So that's the reason I want to fit this model. When I am trying to fit a graph for this, I'll use this serve fit function, wherein I'll take the dependent variable as my survival variable z and independent variable as fit serve dollar where, which will tell me individually for each. So z is also individually for each. So it will tell me this kind of information. So the dependent variable versus the independent variables, and the data that I am taking is Virat. Now I'll get my km. So the km now is nothing but it is doing a fitment. There are 95 n where equal to 2, where equal to 3. So there are 74 such kind of events where the out has occurred. The median is 50. The lower, so 50 balls is the median for the out to happen. 35 is the lower control limit and 73. So typically the approximate number of balls, the median, right? The median number of, on an average, 35 to 73 balls before getting out in the second innings, whereas on an average it is 22 to 63 balls with a median of 35 when he is batting in the first inning. So that is what is the typical serve fit function typically giving me as an output. Whereas I can very well do the plotting of that serve fit as well. So I'll do the plot of Km, right? I can differentiate it. Probably let me put two different colors. Let me first see what this Km is directly coming up. So wherein on the x-axis we are having the time and y-axis we are talking about the status. So because both of them are showing the same way, I would like a slightly improvised version in this Km. So first we'll set two different colors. Green comma red. So one of them would be green, the other one would be red. If you want, I can very well go ahead in terms of even setting the legend and all that stuff as well. So it looks like this. This is the survival model. You could see that the green is associated with 2, which is the second innings, and the red is associated with the first innings. And we could also see that there is a slightly a higher level of survival before getting out in case of the second innings when compared to the first innings, right? And probably I can very well plot the legend to this. I can very well plot the legend to this, wherein I am bringing out at some location. So let me bring it at the location 20 comma 0.2. Let me bring the legend at this x value 20, y value 0.2. Then the legend values per se, I have to give as two important things out here. The first one is the second innings, and the other one is the first innings. So this is what is the legend text, and I am also giving the line colors I have to give. The color is coming out to be green and red, and I have to say the line type equal to 1. So these are the things I am giving as a part of the legend. What has happened? Oh, color equal to, I have to give C off. Okay. So now let me see what has happened to the legend. Yes. So we are getting the second innings is indicated with a green and the first innings is indicated with a red. Now, how do we really interpret it? Right? Okay, if I really want to say what is the chance that he will survive for 20 balls? What is the chance that Virat Kohli will survive for 20 balls? Now, if I go ahead and do the go ahead and interpret from the graph, if he is playing in the first innings, the chances are 60% that he will survive for at least 20 balls. Whereas if he is playing in the second innings, it's close to 75% that he will survive 20 balls. right? What is the probability that he will survive for at least 100 balls? If he is playing in the first innings, it's around 15% or so. But if he is playing in the second innings, it would be more than 25%. So you could very well say that his survival rates are much higher in the second innings compared to that of first innings. Which is but it has nothing to do with home, away. No other features are really influencing his play. It's only the first innings versus second innings where you could see a clear-cut differentiation in the way he plays. So finally, we could clearly conclude that across the path, there is no overlap anywhere in the tree. So it's a very clear indication that his chances of survival are much better when he is playing in the second innings. Chances of not getting out are much better in when he is playing in the second innings compared to that of the first innings. That's one important conclusion that we can bring out by using the survival decision tree models here as a part of our understanding of the decision trees, right? So that's how we want to look at the survival decision trees using the exponential algorithm. Then we will move on to the another important algorithm in this context, which will do the similar kind of a process, which is the conditional inference survival tree. It's also a non-parametric regression tree, but it is embedding the tree structure regression models in it. So this can be executed through the party function, party package with the C tree function again. Right, we have used C tree for various activities till now. So let's load the party function as well again. Okay, the party function is loaded now. We'll use the C tree again. So, but here also it requires the same survival response variable. So I will not create it again because we have already created Z, which is based on the status as well as the time taken for a particular event. So Z is a survival object which we have already created using the survival package, and data is a sample of explanatory variables. So we'll directly go ahead in terms of the execution out here, right? Because the only difference here is the model is different, all the initial steps are similar. So we will, I think we have already taken care of all these activities. This is done, this is done, this is done, this is done. Perform transformation. Now we have already created a survival object based on time and status. Now let's plot the decision tree, right? Fit and plot. So I'll call it as fit conditional. So let me call it as C tree, conditional inference survival tree. So conditional survival tree, let me call it as CS tree. Conditional survival tree, where the function that I am using is the C tree that we have used earlier, but here the response variable needs to be a survival variable. Z tilde, I have to give some of the variables. So let's say I am still giving position plus innings plus home away. I'm giving again all these three as the input parameters, wherein I'm giving the data is coming from Virat. That's it. I have to give as an input here. I don't need to specify the method or something. The moment my Z itself is a survival variable, that itself is sufficient for understanding the process. So let's see what has really come out of this model. Oh, there is no tree structure at all. All 167 are treated in a similar way. Then better let me remove some things out here. Let me try removing the position from the model to see whether there is any kind of an improvement. No, even in this case it looks the same. So better let me remove even the home and away from the model. So at least definitely it will give it separately for innings 1 versus innings 2, but we will get the same data which we have got even with the EXP algorithm, right? Because you could see out here 72 versus 95. So it has really given a small split right there, but when we are going with a combination of variables, it did not even do a split. The conditional inference tree did not do even any kind of a split out there. So let me see if I have gone with a plot for this where I had two trees, two nodes. So this is how the plot directly comes out. That's the advantage, right? Obviously, there to some extent we can compare, but the comparison is slightly difficult when we are having it them in two different graphs altogether. But yes, to some extent you can make out, right? If we are talking about the 50%, here it is coming out. So you have to draw the graph on either sides to really make out some significant differences between the two. But at least it will show a higher level understanding. If you see here, here it is left out at this stage, whereas here we are seeing it going much down. So there is some level of improvement in case there is an increase in the probability of survival in case of the node 3, which is talking about the second innings, whereas much lesser in case of the first innings. So let's see what internal nodes they are reporting the p-value. So if this p-value is lesser than 0.05, it's a clear indication that the split is a significant split. But if the p-value is greater than 0.05, I can very well ignore the splitting criteria. So here the splitting based on the innings is a significant split. The leaf nodes are giving me the number of subjects. So there is a 72 here, 95 here, and a plot of the estimated survival curve. So I am getting the survival curve in both the cases. So what is the chance of survival, let's say for 60 balls in the first innings versus 60 balls in the second innings? I can get it from the survival model. And I can also get the print function, right? If I am doing the print, of course, again it will give me the same as fitcs3, but I can get the same using the print function as well, the same thing, right? 167 observations. So that's also one more important thing that I'm getting. I can also get the where of it to see how many of them are there in each of the leaf nodes, as we have already discussed earlier, right? If I say fit cs3 dollar where, now here I have to give it as where of fit cs3. So you will see some of them into the node 2, some of them into the node 3, and so on. And I can very well create a table of this where function. So there are 72 people falling, there are 72 instances which are falling into node 2, which is typically the first innings, and there are 95 instances that are falling into the node 3, which are into the first innings. Now you can very well go ahead in terms of plotting the tree just like the way we have plotted earlier, right? We can very well get tree response. Just look at one more function called tree response here, a class for representing the binary trees. So if you simply take S tree as tree response of fit CS tree, so S tree typically is giving you for each one, for each out of the 167, it is typically giving you an object where you are going ahead with a separate fitment, the binary tree for each of the object, which is giving me a class of the survival fit object. So overall, you can very well go ahead in terms of doing the plotting for each of the nodes, right? If you want to go with a node tree or whatever, for each of the nodes, you can very well go ahead in terms of fitting an S3 object, and we can very well get a 95% confidence intervals, etc. So graphical displays can very well be improvised in that process as well. But the major input out here is you could clearly see that based on the different covariates that you are providing, based on the different factors that you are providing, the survival analysis is being done separately for each of the groups, and that is what is the benefit that we get out of the survival trees, right? So this is what I wanted to cover as a part of this session. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.